Imagine reaching into the solar system and simply removing one planet, plucking it from existence, like taking a piece from a cosmic puzzle. Would the remaining planets notice? Would orbits shift? Would Earth's climate change? The answer is far more dramatic than you might expect. Our solar system isn't a random collection of worlds spinning independently through space. It's a precisely balanced gravitational dance that's been choreographed over 4.6 billion years. Every planet pulls on every other planet. Jupiter's gravity influences Earth's orbit. Saturn affects Mars. Even tiny Mercury contributes to the overall stability. Tonight, we'll explore what would happen if we removed each planet one by one. We'll discover how Jupiter acts as a cosmic shield, protecting Earth from asteroid impacts. We'll see how Neptune's absence might destabilize the outer solar system, sending comets careening inward. We'll learn why removing Venus could actually make Earth's orbit more chaotic, not less. We'll examine the gravitational resonances, mathematical relationships between orbital periods that keep planets stable. We'll explore how even distant Uranus affects objects in the asteroid belt. And we'll confront the surprising truth. Removing almost any planet would have consequences, some subtle, some catastrophic. This is the story of cosmic interconnection, where gravity links everything to everything else, and disturbing the balance reveals just how delicate planetary stability really is. Before we start removing planets, we need to understand how the solar system works as an interconnected system. It's not just planets orbiting the Sun independently, it's a complex gravitational network where every body influences every other body. The Sun contains 99.86% of the solar system's mass. Its gravity dominates, keeping planets in their orbits. But planets also pull on each other. Jupiter, being the most massive planet at 318 Earth masses, exerts significant gravitational influence. Saturn, Uranus, and Neptune, the other giant planets, also contribute. Even Earth, Venus, and Mars pull on each other noticeably. These mutual gravitational interactions create what scientists call perturbations. A perturbation is a deviation from a perfect elliptical orbit caused by gravitational forces other than the Sunday. Over time, perturbations can accumulate, causing orbital parameters to change slowly. The solar system has evolved over billions of years into a relatively stable configuration. Planets have settled into orbits that, while not perfectly circular or perfectly stable forever, are stable on timescales of millions to billions of years. This stability emerges from the specific masses, positions, and velocities of all the planets working together. One key feature creating stability is orbital resonances. A resonance occurs when two orbiting bodies have orbital periods that are simple ratios like 2:1 or 3:2. Neptune and Pluto are in a 3:2 resonance. Neptune completes 3 orbits for every 2 of Pluto's. This resonance prevents close encounters, even though their orbits cross. Resonances can be stabilizing or destabilizing depending on the specifics. The asteroid belt contains gaps called Kirkwood gaps, where asteroids are absent due to destabilizing resonances with Jupiter. Jupiter's gravity has cleared these regions over millions of years, ejecting asteroids that wandered into resonant orbits. The inner planets Mercury, Venus, Earth, and Mars orbit relatively close together. They interact gravitationally, causing long-term changes in orbital eccentricity and inclination. These changes are cyclical, varying over periods of tens of thousands to millions of years, and are responsible for some of Earth's climate cycles. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are more widely spaced but still interact. Jupiter and Saturn, in particular, have a near resonance. Jupiter orbits about 2.5 times for every Saturn orbit. This near resonance causes periodic perturbations that affect both planets and influence the entire outer solar system. Computer simulations of solar system dynamics reveal that the current configuration is somewhat special. If you run simulations with slightly different initial conditions, planets in slightly different positions or with slightly different masses, many configurations become unstable within millions of years. Planets collide, get ejected, or have their orbits radically altered. Our solar system has survived 4.6 billion years without major catastrophes. Mercury has a somewhat chaotic orbit that might become unstable in a few billion years, potentially colliding with Venus or being ejected. But for now, the system is stable enough that we can predict planetary positions centuries into the future with high accuracy. This stability is not guaranteed, though. It's contingent on all the planets being where they are with the masses they have. Removing a planet, especially a massive one like Jupiter, would disturb the balance. The remaining planets would need to adjust to a new gravitational environment, and that adjustment could be chaotic. Another important concept is the invariable plane, the plane perpendicular to the total angular momentum of the solar system. The planets orbit close to this plane, with small inclinations. This near coplanarity reduces gravitational interactions and contributes to stability. If a massive planet were removed, the invariable plane would shift slightly, and planetary inclinations relative to the new plane would change. Gravitational interactions also affect objects beyond the planets. The asteroid belt between Mars and Jupiter contains millions of rocky bodies. Jupiter's gravity dominates the belt, creating structure through resonances and preventing the asteroids from coalescing into a planet. The Kuiper belt beyond Neptune contains icy bodies, including dwarf planets. Neptune's gravity shapes the Kuiper belt, shepherding objects and creating resonances. The Oort cloud, a vast spherical shell of comets surrounding the solar system at distances up to 100,000 AU, is loosely bound. Passing stars can perturb Oort cloud comets, sending them into the inner solar system. Changes in planetary orbits could also affect the Oort cloud's stability. Understanding this interconnected system helps us predict what happens when we remove a planet. The effects depend on which planet we remove, its mass, its location, and its current gravitational relationships with other bodies. With this foundation, we can now explore the consequences of removing each planet, starting with the innermost and working outward. What happens if we remove Mercury, or Venus, or most dramatically Jupiter? Let's find out. Mercury is the smallest planet, with only 5.5% of Earth's mass. It orbits closest to the Sun, completing an orbit every 88 days. Its gravity is weak, and it doesn't have moons or rings. You might think removing Mercury would barely affect the rest of the solar system. Surprisingly, even Mercury matters. Mercury's orbit is unusual. It has the highest eccentricity of any planet, meaning its orbit is more elliptical than others. It also has a significant orbital inclination 7 degrees to the ecliptic plane. These features make Mercury's orbit less stable than other planets. In fact, Simulations show that over the next few billion years, Mercury's orbit might become chaotic, possibly leading to ejection or collision with Venus. If we removed Mercury today, the most immediate effect would be on Venus. Venus and Mercury are gravitationally coupled. Mercury's gravity causes small perturbations in Venus's orbit. These perturbations are tiny but accumulate over time. Without Mercury, Venus's orbital parameters would evolve slightly differently. Computer simulations suggest that removing Mercury might actually make Venus's orbit slightly more stable in the very long term. Mercury's chaotic orbit introduces small instabilities that propagate through the inner solar system. Without that source of chaos, the inner planets might settle into marginally more stable orbits. However, the effect is small. Venus would hardly notice Mercury's absence over millions of years. Earth would notice even less. The gravitational influence of Mercury on Earth is minuscule, far smaller than the influence of Venus or Jupiter. But there's an indirect effect. Mercury plays a role in the complex dance of resonances and near resonances among the inner planets. The orbital periods of Mercury, Venus, Earth, and Mars are related in complicated ways that create long-term stability. Remove one piece and the pattern changes. Specifically, Mercury's orbit precesses its ellipse slowly rotates in space. This precession is caused by general relativistic effects and perturbations from other planets. The rate of precession creates relationships with the precession rates of Venus and Earth. These relationships contribute to the overall stability pattern of the inner solar system. Without Mercury, the precession patterns of Venus and Earth would change slightly. Over millions of years, this could affect how eccentricity and inclination vary for Venus and Earth. The changes would be small, Earth's orbit would remain stable and habitable, but there might be subtle differences in climate cycles driven by orbital variations. Mercury also plays a minor role in stabilizing the asteroid belt. Some asteroids have orbits that bring them near Mercury, and Mercury's gravity can deflect these asteroids. Without Mercury, a few more asteroids might reach Venus-crossing or Earth-crossing orbits. The increase would be tiny, perhaps a handful more asteroids over millions of years, but it's a measurable effect. One interesting consequence involves the Yarkovsky effect, a force on small asteroids caused by uneven thermal radiation. The Yarkovsky effect depends on the asteroid's orbit and the gravitational environment. Removing Mercury would change the orbits of some near-Sun asteroids, altering their Yarkovsky-driven evolution. This could change which asteroids eventually become Earth crossers. Mercury has no moons, no ring system, no significant debris. Removing it wouldn't leave behind a cloud of material. The planet would simply disappear, taking its small gravitational influence with it. What about the Sun itself? Mercury's gravity pulls on the Sun, causing the Sun to wobble slightly. This wobble is tiny, far smaller than the wobble caused by Jupiter, but it exists. Removing Mercury would eliminate that wobble, but no other body in the solar system would notice. If we removed Mercury instantly, the lack of its gravitational pull would propagate outward at the speed of light. Venus, being closest, would feel the change in about 3.6 light minutes, the time it takes light to travel from Mercury to Venus. Earth would feel it about 6 light minutes later. Jupiter would notice about 30 light minutes later. The change would be the sudden absence of a small gravitational tug, causing infinitesimal shifts in orbital velocities. These shifts would be almost immeasurably small. To detect Mercury's removal from Earth, you'd need extraordinarily precise measurements of planetary positions over years or decades. The effect on Earth's orbit would be a change of perhaps a few meters in position over a year, negligible compared to our 150 million kilometer orbital radius. Over hundreds of millions of years, however, the absence of Mercury would have cumulative effects. The inner solar system would evolve slightly differently. Venus might avoid a close encounter with Mercury that would have happened in some distant future timeline. Earth's orbital eccentricity might vary within a slightly different range, potentially affecting ice age cycles. The most significant effect of removing Mercury would be symbolic rather than physical. Mercury is part of the solar system's inventory, and its presence contributes to the overall system. Its absence would represent a discontinuity in the orderly progression of planetary distances from the Sun. But realistically, if we removed Mercury, most of the solar system wouldn't care. Venus would notice slightly, Earth would barely notice. Mars, Jupiter, and everything beyond wouldn't notice at all in any practical sense. Mercury is the least consequential planet to remove. That said, least consequential doesn't mean no consequences. Even Mercury, small and distant from most of the solar system, is gravitationally connected to everything else. Removing it would change the system, even if subtly. Next, let's consider a more massive target, Venus. Venus is the second planet from the Sun and the closest planet to Earth. With 81.5% of Earth's mass, Venus is substantial enough that removing it would have noticeable effects. Venus orbits the Sun every 225 days at an average distance of 108 million kilometers. It comes closer to Earth than any other planet within 38 million kilometers at closest approach. This proximity means Venus's gravity significantly affects Earth's orbit. If we removed Venus, Earth would feel the change immediately, or rather, about 6 light minutes later, when the information propagates at light speed. Earth's orbital velocity would shift slightly as Venus's gravitational pull vanished. The shift would be small, but over time, it would compound. The most significant effect of Venus's removal would be on Earth's long-term orbital stability. Venus and Earth are gravitationally locked in a complex relationship. Their orbits interact through resonances and near-resonances that cause periodic variations in eccentricity, inclination, and orbital precession. These variations occur over cycles of tens of thousands to millions of years. They're responsible for some of Earth's climate cycles. The Milankovitch cycle's variations in Earth's orbit that drive ice age timing involve changes in eccentricity, obliquity, axial tilt, and precession. Venus's gravity influences these cycles. Without Venus, Earth's orbital variations would change. Computer simulations suggest that removing Venus might actually make Earth's orbit more chaotic in the long term. Venus's presence currently has a stabilizing effect, helping to dampen extreme variations in Earth's eccentricity. Specifically, without Venus, Earth's eccentricity could vary over a wider range. Instead of staying between about 0 and 0.058, nearly circular to slightly elliptical, over a 100,000-year cycle, Earth's eccentricity might swing higher, perhaps reaching 0.08 or more. This would make Earth's orbit more elliptical. A more elliptical orbit means greater seasonal variation. When eccentricity is high, the difference between Earth's closest approach to the Sun, perihelion, and farthest distance, aphelion, is larger. Currently, Earth receives about 7% more solar energy at perihelion than aphelion. With higher eccentricity, this difference would increase. Higher eccentricity could lead to more extreme seasons, particularly in one hemisphere. Currently, Earth is closest to the Sun during Northern Hemisphere winter, which moderates northern winters slightly. If eccentricity increased, this effect would strengthen, potentially disrupting climate patterns. The changes wouldn't happen quickly. Over thousands to millions of years, Earth's orbit would gradually evolve along a different trajectory than it would with Venus present. The immediate climate effects would be negligible, but over deep time, the planet's orbital history would diverge. Venus's removal would also affect Mercury. Mercury and Venus interact gravitationally, and Venus's presence helps constrain Mercury's chaotic orbit somewhat. Without Venus, Mercury's orbit might become unstable more quickly, potentially colliding with the Sun, colliding with what remains at Venus's former position, or being ejected from the inner solar system. Mars would also feel Venus's absence, though less dramatically. Venus contributes to the gravitational environment that shapes Mars's orbit. Without Venus, Mars's orbital evolution would shift slightly. Mars already has a highly variable obliquity. Its axial tilt can swing from near 0 degrees to over 60 degrees over millions of years, unlike Earth's stable 23.5 degrees. Venus's absence might make Mars's obliquity variations even wilder. The asteroid belt would experience minor changes. Venus's gravity affects some asteroids, particularly those in orbits that bring them near Venus. Without Venus, these asteroids would follow slightly different paths. Some might become Earth crossers sooner, while others might avoid Earth-crossing orbits they otherwise would have entered. One specific concern is Venus family asteroids whose orbits bring them near Venus regularly. Without Venus to perturb them, these asteroids would disperse along different trajectories. A few might eventually encounter Earth, slightly increasing the long-term impact risk. Venus has no moons, so removing it wouldn't leave orphaned satellites. It doesn't have a ring system either. The removal would be clean one moment, Venus is there, the next it's gone. The Sun would notice Venus's absence through a reduction in the solar wobble. Venus's gravity causes the Sun to move in a small circle, shifting the solar system's center of mass away from the Sun's center. Without Venus, this wobble would decrease slightly. The change would be small compared to Jupiter's wobble, but larger than Mercury's. From Earth, Venus's removal would have one immediate, obvious effect. We'd lose the brightest object in the night sky besides the Moon. Venus is often called the morning star or evening star because of its brilliant appearance at dawn or dusk. Its absence would be noticed by casual skywatchers immediately. For scientists studying the solar system's dynamics, Venus's removal would be a major event. Venus is a key piece in understanding terrestrial planet formation and evolution. It's often called Earth's twin because of similar size and mass, despite radically different conditions. Losing Venus would eliminate a crucial comparison point for planetary science. In terms of gravitational dynamics, Venus is substantial enough that its removal would measurably alter the solar system's evolution. Unlike Mercury, whose removal is almost inconsequential, Venus's absence would change Earth's future orbital history in potentially significant ways. The irony is that Venus, so similar to Earth in many ways, actually helps keep Earth's orbit stable. Remove Earth's twin, and Earth itself might become more chaotic over time, not immediately, not catastrophically, but noticeably over millions of years. Next, let's consider the most dramatic removal. What happens if we take out the solar system's largest planet, Jupiter? Jupiter is a giant among planets, literally. With 318 Earth masses and 2.5 times the mass of all other planets combined, Jupiter dominates the solar system's planetary dynamics. Removing Jupiter would have profound, system-wide consequences. Jupiter orbits the Sun every 11.9 years at an average distance of 5.2 AU. Despite being far from Earth, Jupiter's gravity significantly influences Earth's orbit and the orbits of all other planets. Jupiter also plays critical roles in shaping the asteroid belt, protecting the inner planets from comets, and maintaining stability in the outer solar system. If we removed Jupiter, the effects would cascade through the entire solar system. Let's explore them region by region. Effects on the inner planets. Earth's orbit would change noticeably. Jupiter's gravity causes periodic perturbations in Earth's eccentricity and inclination. These perturbations follow a roughly 100,000-year cycle, one of the Milankovitch cycles that influence Earth's climate and ice age timing. Without Jupiter, this cycle would disappear. Earth's orbital variations would be driven primarily by Venus and Mars, leading to different patterns. Computer simulations suggest Earth's eccentricity might vary less predictably, potentially making climate cycles more chaotic. Jupiter also affects Earth's obliquity axial tilt. Earth's 23.5-degree tilt is stabilized by the Moon's gravity. But Jupiter's gravity also plays a role in long-term obliquity variations. Without Jupiter, Earth's axial tilt might vary more over millions of years. Though the Moon would still provide significant stabilization, Mars would be dramatically affected. Mars lacks a large moon to stabilize its obliquity, so its axial tilt varies chaotically between 0 and 60 degrees over millions of years, driven largely by planetary perturbations. Jupiter is a major contributor to these variations. Without Jupiter, Mars's obliquity variations would change significantly. Some simulations suggest Mars might have a more stable obliquity, varying less wildly. Others suggest the variations might follow different patterns but remain chaotic. Either way, Mars's climate history over billions of years would be fundamentally different. Venus and Mercury would be less affected but would still notice Jupiter's absence. Jupiter contributes to the overall gravitational environment that shapes inner planet orbits. Without it, the inner planets would settle into slightly different long-term orbital evolution patterns. Effects on the asteroid belt. Jupiter's removal would transform the asteroid belt. Jupiter's gravity currently dominates the belt, creating structure through resonances. The Kirkwood Gaps regions where asteroids are absent exist because of destabilizing resonances with Jupiter. Asteroids in these resonances get ejected from the belt over millions of years. Without Jupiter, the Kirkwood Gaps would gradually fill in. Asteroids would drift into these regions, and without Jupiter's resonances to clear them, they'd remain. Over millions of years, the asteroid belt would become more uniform, without the current gaps and density variations. Jupiter also prevents asteroids from coalescing into a planet. The asteroid belt contains enough material to form a planet about half Mars's mass, but Jupiter's gravitational perturbations stir up asteroid velocities, making collisions more destructive than constructive. Without Jupiter, asteroid collision velocities would decrease, potentially allowing asteroids to accrete into larger bodies. Over hundreds of millions of years, the asteroid belt might produce a small planet, perhaps Mars-sized. This planet would form where the asteroid density is highest, probably in the inner belt around 2.5 AU. The process would be slow because the total mass is limited and asteroids are spread over a large volume. The formation of an asteroid belt planet would further alter the solar system's dynamics. This new planet would gravitationally interact with Mars and Jupiter's former neighbors Saturn and the inner planets. The solar system's configuration would evolve in unpredictable ways. Effects on the outer planets. Saturn would be profoundly affected by Jupiter's removal. Jupiter and Saturn have a near resonance. Jupiter orbits about 2.49 times for every Saturn orbit, close to a 5:2 ratio. This near resonance causes significant gravitational interactions between the two gas giants. Without Jupiter, Saturn would suddenly be the dominant planet in the outer solar system. Its orbit would evolve differently without Jupiter's gravitational influence. Saturn's eccentricity and inclination would shift over time, settling into a new pattern. Uranus and Neptune would also change. All four giant planets interact gravitationally, creating a complex dance that maintains outer solar system stability. Remove one planet, especially the most massive, and the remaining three would need to adjust. Computer simulations of the outer solar system without Jupiter show that the remaining giant planets' orbits become less stable. Over tens of millions of years, Saturn, Uranus, and Neptune might develop higher eccentricities and inclinations. In some simulations, Neptune could be ejected from the solar system entirely over hundreds of millions of years. The NICE model of solar system formation suggests that the outer planets originally formed closer together and migrated outward due to interactions with a disk of planetesimals. Jupiter's presence was crucial in driving this migration. Without Jupiter from the beginning, the solar system would have formed completely differently. But if we remove Jupiter now, after the system has stabilized, we're disrupting billions of years of gravitational choreography, effects on the Kuiper belt and beyond. Neptune's gravity shapes the Kuiper belt, creating resonances and structure. But Jupiter influences the Kuiper belt indirectly by affecting Neptune's orbit. Without Jupiter, Neptune's orbit would evolve differently, changing how Neptune shepherds Kuiper belt objects. Some Kuiper belt objects might be destabilized, either being sent into the inner solar system as comets or ejected outward. The population of short-period comets with orbits controlled by Jupiter's gravity would change dramatically. These Jupiter family comets would no longer have Jupiter to gravitationally capture them, and many would follow different paths. The Oort cloud, far beyond Neptune, would be less directly affected, but changes in the giant planets' orbits could have subtle effects on Oort cloud stability over millions of years. Jupiter as a comet shield. One of Jupiter's most important roles is acting as a comet shield for the inner solar system. Jupiter's massive gravity captures or deflects many comets that would otherwise reach the inner planets. Without Jupiter, more comets would impact Earth, Mars, Venus, and Mercury. Jupiter's gravitational influence works in several ways. First, it can capture comets into Jupiter family orbits, short-period comets that loop between Jupiter and the Sunday. These captured comets never reach the inner planets because Jupiter controls their orbits. Without Jupiter, these comets would follow different paths, potentially encountering Earth. Second, Jupiter can deflect comets onto different trajectories. A comet approaching from the outer solar system might be bent by Jupiter's gravity, changing its path so it misses Earth entirely or even gets ejected from the solar system. Without Jupiter, these comets would continue undeflected, following their original paths. Third, Jupiter can act as a gravitational vacuum cleaner, actually colliding with comets and removing them from the solar system entirely. The Shoemaker-Levy 9 event in 1994 dramatically demonstrated this. The comet broke apart under Jupiter's tidal forces and slammed into Jupiter's atmosphere, creating massive impact scars visible from Earth. If Jupiter hadn't been there, that comet or one of its fragments might have continued into the inner solar system. The increase in comet impacts on Earth would be significant, perhaps double or triple the current rate. Over Earth's history, this could mean dozens or hundreds more major impacts, some potentially catastrophic for life. The impact that killed the dinosaurs 66 million years ago was probably an asteroid. But if comet impacts had been more frequent throughout Earth's history, life's evolution might have been disrupted by additional mass extinctions. Computer simulations of solar systems without Jupiter-like planets show dramatically higher impact rates on terrestrial planets. Earth-like planets in such systems experience impacts perhaps 5 to 10 times more frequently than Earth does. This has implications for the habitability of exoplanet systems. Without a protective giant planet might be hostile to complex life due to frequent catastrophic impacts. Jupiter's role as a shield isn't perfect. Sometimes Jupiter's gravity sends comets inward rather than outward. Some comets are actually deflected toward Earth by Jupiter's influence. But statistically, Jupiter removes more comets than it sends inward, providing net protection. The protection extends to all inner planets. Venus, Earth, and Mars all benefit from Jupiter's presence. Without Jupiter, Venus might have even thicker atmosphere from comet impacts adding volatiles. Mars might have lost its remaining atmosphere to impacts more quickly. Mercury would be more heavily cratered than it already is. This protective role makes Jupiter crucial not just for orbital dynamics, but for the habitability of the inner solar system. Life on Earth has flourished partly because Jupiter has reduced the impact rate to manageable levels. Remove Jupiter, and Earth would be a more dangerous place, with catastrophic impacts occurring more frequently. Effects on spacecraft and human space exploration. Jupiter is used for gravity assists by spacecraft heading to the outer solar system. Removing Jupiter would eliminate this tool for mission planners. Reaching Saturn, Uranus, Neptune, or the Kuiper Belt would require more fuel or longer flight times. For human space exploration, Jupiter's moons, particularly Europa with its subsurface ocean, are prime targets in the search for extraterrestrial life. Removing Jupiter would remove these moons as well, eliminating an entire category of astrobiological targets. Summary of Jupiter's removal. Removing Jupiter would fundamentally alter the solar system. Earth's orbit would become less stable over millions of years. Mars's obliquity variations would change. The asteroid belt would evolve into a more uniform disk and might even form a small planet. Saturn, Uranus, and Neptune would become less stable, with Neptune possibly being ejected. The inner solar system would face increased comet bombardment. Of all the planets, Jupiter's removal would have the most far-reaching consequences. Jupiter is the solar system's gravitational anchor for everything beyond Mars. Without it, the system would be unrecognizable over millions of years. Next, Let's examine what happens if we remove Jupiter's smaller sibling, Saturn. Saturn is the second largest planet, with 95 Earth masses. It orbits at 9.5 AU, taking 29.5 years to complete one orbit. While smaller than Jupiter, Saturn still plays an important role in solar system dynamics, particularly through its near resonance with Jupiter and its influence on the outer solar system. If we removed Saturn, the most immediate effect would be felt by Jupiter. Jupiter and Saturn's near 5:2 resonance. Jupiter completes 5 orbits for every 2 of Saturn's, approximately creates periodic gravitational interactions. These interactions cause both planets' orbits to vary slightly over thousands of years. Without Saturn, Jupiter's orbit would stabilize somewhat. The periodic variations driven by the Jupiter-Saturn interaction would cease. Jupiter's eccentricity would settle into a slightly different average value, and its orbital parameters would evolve more smoothly. However, this might not be entirely beneficial for the solar system. The Jupiter-Saturn interaction helps maintain stability in the outer solar system by preventing other resonances from becoming dominant. Without Saturn to interact with Jupiter, other perturbations might grow, potentially destabilizing Uranus or Neptune over millions of years. Uranus and Neptune would definitely notice Saturn's absence. Currently, all 4 giant planets interact in a complex 4-body problem. Saturn contributes to this interaction by affecting Neptune and, to a lesser extent, Uranus. Without Saturn, Neptune's orbit would evolve slightly differently. Neptune might migrate inward or outward over millions of years, depending on how gravitational interactions with Jupiter and Uranus change. This migration would affect the Kuiper belt, potentially destabilizing some Kuiper belt objects and sending them into the inner solar system as comets. Uranus would also change its orbit, though perhaps less dramatically than Neptune. Uranus is between Jupiter and Neptune gravitationally, and it mediates some of the interactions between these planets. With Saturn removed, the Uranus-Neptune interaction would change, potentially affecting both planets' long-term stability. Saturn has an extensive ring system, the most prominent in the solar system, and dozens of moons. Removing Saturn would also remove these rings and moons. The rings contain countless icy particles orbiting Saturn. If Saturn disappeared, these particles would suddenly be in independent orbits around the Sun. Most ring particles would disperse, spreading out along Saturn's former orbital path. Over time, they'd form a diffuse disk of debris at 9.5 AU. Some particles might be gravitationally perturbed by Jupiter or the other giant planets, potentially creating a new asteroid-like population in the outer solar system. Saturn's moons, particularly Titan, are scientifically important. Titan is the second largest moon in the solar system and has a thick atmosphere, liquid methane lakes, and potential subsurface ocean. Removing Saturn would remove Titan, eliminating another astrobiological target. Saturn's other moons, Enceladus with its subsurface ocean, Iapetus with its mysterious equatorial ridge, Mimas resembling the Death Star, would all vanish. These moons would disappear along with Saturn if the planet were removed, taking their scientific value with them. For the inner planets, Saturn's removal would have minimal direct effects. Saturn is far enough away that its gravitational influence on Earth, Mars, Venus, and Mercury is weak. Over millions of years, the cumulative effects of Saturn's absence might slightly alter inner planet orbits, but the changes would be small compared to Jupiter's influence. The asteroid belt would barely notice Saturn's removal. Jupiter dominates the asteroid belt gravitationally, and Saturn's influence is minor. Some asteroids in the outer belt might be affected slightly, but the overall structure of the asteroid belt would remain largely unchanged. One interesting consequence involves long-period comets, comets with orbital periods of hundreds to thousands of years. Some of these comets have aphelions, farthest points, near Saturn's orbit. Saturn's gravity can perturb these comets, changing their orbits. Without Saturn, these comets would follow slightly different paths on subsequent passages through the solar system. A few long-period comets might become short-period comets that interact primarily with Jupiter instead of Saturn. Others might be ejected from the solar system or sent into the inner solar system more frequently. The changes would be modest but measurable over thousands of years. Saturn's removal would affect our view of the night sky. Saturn is visible to the naked eye as a bright star that moves against the background constellations. Through telescopes, Saturn's rings make it one of the most beautiful celestial objects. Losing Saturn would deprive humanity of one of the iconic sights in astronomy. For spacecraft exploration, Saturn is an important destination. The Cassini mission provided 13 years of detailed observations of Saturn, its rings, and moons. Future missions to Titan or Enceladus are being planned. Removing Saturn would eliminate these exploration opportunities. From a gravitational dynamics perspective, Saturn is important but not as critical as Jupiter. Its presence contributes to outer solar system stability, and its removal would change how the outer planets interact. But the solar system wouldn't collapse without Saturn. The remaining planets, particularly Jupiter, would maintain most of the current structure. The key point is that Saturn's role is more about fine-tuning than fundamental structure. Jupiter provides the dominant gravitational influence in the outer solar system. Saturn adds complexity and helps maintain certain resonances and stability patterns. Remove Saturn, and the system continues but evolves differently. Saturn's removal would be less dramatic than Jupiter's, but more significant than removing an inner planet. The outer solar system would change noticeably, while the inner solar system would barely feel it. Next, let's consider the ice giants. What happens if we remove Uranus or Neptune? Uranus and Neptune are the ice giants, less massive than Jupiter and Saturn, but still substantial. Uranus has 14.5 Earth masses, Neptune has 17 Earth masses. They orbit at 19.2 AU and 30 AU respectively, taking 84 and 165 years to orbit the Sunday. Because they're far from the inner planets and less massive than the gas giants, you might think removing Uranus or Neptune would have minimal effects. However, these planets play important roles in the outer solar system, particularly in shaping the Kuiper belt and influencing long-period comets. Removing Uranus. If we removed Uranus, Neptune would be most affected. Uranus and Neptune interact gravitationally, causing perturbations in each other's orbits. Without Uranus, Neptune's orbital evolution would change slightly. Neptune might migrate inward slightly over millions of years, no longer constrained by Uranus's gravitational presence. This inward migration would affect the Kuiper belt. Neptune currently maintains many Kuiper belt objects in resonances. The Plutinos in 3:2 resonance are the most famous example. If Neptune migrated, these resonances would shift, potentially destabilizing some Kuiper belt objects. Jupiter and Saturn would barely notice Uranus's absence. Uranus is far enough away and small enough that its gravitational influence on the gas giants is minimal. The Jupiter-Saturn interaction would continue unchanged. The inner planets, Earth, Venus, Mars, Mercury, would be completely unaffected in any practical sense. Uranus's gravity doesn't reach the inner solar system in any meaningful way. Uranus has 27 known moons, including interesting worlds like Miranda with its bizarre terrain and Ariel with possible cryovolcanism. These moons would vanish along with Uranus. The planet also has a ring system, though much fainter than Saturn's. The rings and their particles would disperse into independent solar orbits. One interesting aspect of Uranus is its extreme axial tilt, 98 degrees, meaning it essentially orbits on its side. This unusual tilt is thought to result from a massive collision early in the solar system's history. Removing Uranus would eliminate this oddity from the planetary roster. Removing Neptune. Neptune's removal would have more significant effects than Uranus's, primarily because Neptune directly controls the Kuiper belt. The Kuiper belt is a disk of icy bodies beyond Neptune's orbit, extending from about 30 AU to 50 AU. Neptune's gravity shapes this belt through resonances and perturbations. Many Kuiper belt objects are in resonance with Neptune, including Pluto and other Plutinos in 3:2 resonance. Without Neptune, these resonances would disappear. Kuiper belt objects would suddenly be in slightly different orbits, no longer gravitationally locked to Neptune's period. The belt would slowly evolve into a different configuration. Some Kuiper belt objects would drift inward, potentially becoming short-period comets that enter the inner solar system. The flux of comets from the Kuiper belt would increase significantly, perhaps doubling or tripling over millions of years. This increased comet flux would raise impact rates on all inner planets, though not as dramatically as removing Jupiter would. Earth might experience a 20–30% increase in comet impacts over millions of years. While not catastrophic, this would measurably affect Earth's long-term bombardment history. Neptune also scatters some objects outward into the Oort cloud or ejects them from the solar system entirely. Without Neptune, fewer objects would be scattered outward, potentially leaving more material in the Kuiper belt region. Over time, this could lead to more collisions among Kuiper belt objects. Uranus would be affected by Neptune's removal. The two ice giants interact, and without Neptune, Uranus's orbit would evolve slightly differently. Uranus might migrate outward over tens of millions of years, potentially reaching 20 or 21 AU instead of its current 19.2 AU. Jupiter and Saturn would barely notice Neptune's absence, just as they barely noticed Uranus's. The gas giants are too far away and too dominant gravitationally to be significantly affected by the removal of an ice giant. Neptune has 14 known moons, including Triton, a captured Kuiper belt object with geysers of nitrogen. Triton is scientifically fascinating, possibly harboring a subsurface ocean. Removing Neptune would remove Triton and the other moons, along with Neptune's faint ring system, removing both Uranus and Neptune. If we removed both ice giants, the outer solar system would change dramatically. The Kuiper belt would lose its gravitational shepherds, becoming a more chaotic region. Without Neptune's resonances and Uranus's perturbations, Kuiper belt objects would drift and scatter more freely. Over millions of years, the Kuiper belt might spread out, becoming more diffuse. Some objects would drift inward, increasing the comet flux to the inner solar system. Others might drift outward, becoming scattered disk objects or even joining the Oort cloud. Saturn would become the outermost giant planet, assuming new importance in controlling the outer solar system. However, Saturn is much farther from the Kuiper belt than Neptune, and its gravitational influence there is weak. The Kuiper belt would be more anarchic without the ice giants. Jupiter would also gain importance, becoming the dominant planet for scattering comets and asteroids. But Jupiter is even farther from the Kuiper belt, and its influence is weaker still. The inner solar system would face increased comet bombardment, perhaps 50 to 100% more impacts than currently over geological timescales. This wouldn't be catastrophic for Earth, but it would be noticeable. More large impacts like the one that killed the dinosaurs might occur. Summary: removing Uranus has modest effects, primarily on Neptune and the Kuiper belt. Removing Neptune has more significant effects, particularly on Kuiper belt stability and comet flux. Removing both ice giants would substantially change the outer solar system's dynamics and increase comet impacts on inner planets. The ice giants, while far away and relatively small, still play important roles in maintaining solar system structure. Their removal wouldn't collapse the system, but it would allow the Kuiper belt to become more chaotic and would increase bombardment of the inner planets over time. Having explored removing individual outer planets, let's now return to the inner solar system and consider a planet whose removal might seem minor but has interesting consequences: Mars. Mars is small, only 11% of Earth's mass, barely larger than Mercury. It orbits at 1.52 AU, taking 687 days to complete an orbit. Mars is close enough to Earth that it has some gravitational influence, but weak enough that you might expect its removal to be inconsequential. However, Mars plays a surprising role in Earth's long-term orbital stability. Removing Mars would have subtle but real effects that would accumulate over millions of years. Mars and Earth are gravitationally coupled. Their orbits interact through resonances and near resonances, causing periodic variations in eccentricity and other orbital parameters. These interactions occur over cycles of hundreds of thousands to millions of years. If we removed Mars, Earth's orbital evolution would change. Computer simulations show that Mars actually helps stabilize Earth's orbit somewhat. Without Mars, Earth's eccentricity might vary over a slightly wider range, and the timing of eccentricity variations would shift. The effect is, modest Earth's orbit would remain habitable and relatively stable. But over hundreds of thousands of years, the climate cycles driven by orbital variations, Milankovitch cycles, would differ slightly. Ice ages might have different timing, and the severity of glacial-interglacial cycles might change. Mars's removal would also affect Earth's obliquity, axial tilt, variations. Earth's tilt is primarily stabilized by the Moon, but planetary perturbations also play a role. Mars contributes to these perturbations. Without Mars, Earth's obliquity would vary slightly differently, potentially affecting long-term climate patterns. Venus would also notice Mars's absence. Venus, Earth, and Mars form a gravitational trio in the inner solar system, and their mutual interactions shape all three orbits. Remove Mars, and Venus's orbit would evolve differently, though the changes would be small. Mercury would be less affected. Mercury interacts more with Venus and the Sun than with Mars. Mars's removal would have negligible effects on Mercury's chaotic orbit. The asteroid belt would feel Mars's absence more significantly. Mars is close enough to the asteroid belt that it perturbs some asteroids, particularly those in the inner belt. Mars crossing asteroids whose orbits bring them near Mars would suddenly have one fewer planet to contend with. Without Mars to perturb them, Some asteroids might remain in the inner belt longer before being perturbed by other planets. Other asteroids that would have been scattered by Mars encounters might instead become Earth-crossing, potentially increasing the long-term impact risk for Earth. Mars itself has two small moons, Phobos and Deimos, likely captured asteroids. If Mars disappeared, these moons would suddenly be in independent orbits around the Sunday. Both moons are tiny. Phobos is about 22 kilometers across, Deimos about 12 kilometers. They'd become asteroids, adding to the near-Mars population. Phobos is slowly spiraling into Mars due to tidal forces and will crash into Mars or break apart in about 50 million years. If we removed Mars now, Phobos would be spared this fate, becoming a permanent asteroid instead. Mars has no ring system and no other satellites, so removing Mars wouldn't leave much debris beyond its two tiny moons. From Earth's perspective, Mars's removal would be noticeable in the night sky. Mars appears as a bright red star, visible for much of the year. During opposition, when Mars is closest to Earth, it can be brighter than most stars. Losing this familiar sight would be obvious to skywatchers. For space exploration, Mars is humanity's most studied planet beyond Earth. Dozens of missions have explored Mars, and future human missions are planned. Removing Mars would eliminate the most accessible destination for human space exploration, drastically changing the trajectory of space program development. Mars is also a key piece in understanding terrestrial planet evolution. It's small enough to have cooled and lost its magnetic field, leading to atmospheric loss. Studying Mars helps us understand how planets retain atmospheres and what factors make them habitable. Losing Mars would remove this scientific laboratory. From a gravitational dynamics standpoint, Mars's removal would have subtle effects on the inner solar system. Earth's orbit would become slightly less stable over millions of years. The asteroid belt would lose a nearby perturber, changing some asteroid trajectories. Venus's orbit would evolve slightly differently. None of these effects would be catastrophic. The inner solar system would continue functioning largely as before, but over deep time, millions of years, the cumulative changes would be measurable. Mars occupies an important position in the solar system. It's the last terrestrial planet before the asteroid belt, bridging inner rocky planets and outer giants. It's located at the edge of the habitable zone, making it marginal for life but not impossible. Its position allows it to interact with both Earth and the asteroid belt. Removing Mars would create a gap between Earth at 1 AU and the asteroid belt at 2 to 3.5 AU. This gap would be larger than the current Earth-Mars gap. The inner solar system would feel more separated from the outer system without Mars as a stepping stone. Interestingly, some theories suggest Mars should have been larger. The planet appears to have stopped growing early in the solar system's formation, perhaps due to Jupiter's formation perturbing material away from the Mars region. If Mars had grown to Earth size or larger, the solar system's dynamics would be quite different. In some alternate solar systems discovered around other stars, there are super-Earths at Mars-like distances, rocky planets larger than Earth but smaller than Neptune. Our solar system lacks such a planet, and if Mars had grown larger, it might have filled this niche. But as it is, Mars is small, and removing it would have modest effects. The inner solar system would notice over millions of years, particularly Earth, but wouldn't collapse. Mars's role is more supportive than structural. It helps fine-tune inner planet stability, but isn't essential. Having explored removing each planet individually, let's now consider the broader question. What patterns emerge from these thought experiments, and what do they tell us about solar system architecture? We've explored removing each major planet individually. Now let's step back and identify patterns, examining general principles that govern how planetary removal affects the solar system. Mass matters most. The most obvious pattern. A planet's mass determines how much its removal matters. Jupiter's removal would have the most dramatic effects because Jupiter contains most of the solar system's planetary mass. Saturn's removal would have significant but lesser effects. Removing Neptune, Uranus, or Mars would have modest effects. Mercury's removal would be almost inconsequential. This makes intuitive sense. Gravitational force depends on mass. More massive planets exert stronger gravitational influences on their neighbors. Remove a massive planet and the gravitational environment changes substantially. Remove a low-mass planet and most of the system barely notices. However, mass isn't everything. Location and orbital resonances also matter. Location determines which bodies are affected. A planet primarily affects its neighbors. Venus's removal mostly affects Earth and Mercury. Jupiter's removal affects everything inner planets through perturbations, the asteroid belt directly, and outer planets significantly. Neptune's removal primarily affects the Kuiper belt. This reflects how gravitational force falls off with distance. Planets close to a removed planet feel the change most strongly. Planets far away feel little effect. Location also determines a planet's role in the system's architecture. Jupiter sits between the inner rocky planets and outer icy regions, making it a natural dividing line. Neptune sits at the edge of the Kuiper belt, making it the shepherd of that region. Each planet occupies a niche, and removing it disrupts that niche. Resonances create stability and instability. Orbital resonances, simple ratios between orbital periods, play crucial roles. The Jupiter-Saturn near 5:2 resonance affects both planets. Neptune's 3:2 resonance with Pluto and other Plutinos shapes the Kuiper belt. Inner planet near resonances affect long-term stability. When you remove a planet, you remove its resonances. Bodies locked in resonance with the removed planet suddenly find themselves in non-resonant orbits. This can destabilize them, sending them on new trajectories. Conversely, removing a planet can also remove destabilizing resonances. The Kirkwood gaps in the asteroid belt exist because Jupiter's resonances destabilize certain orbits. Remove Jupiter, and these destabilizing resonances disappear, allowing asteroids to fill the gaps. Timescales matter. The effects of planetary removal unfold over different timescales. Immediate effects, the sudden absence of a gravitational tug, happen within light travel time. Short-term effects, orbital adjustments, happen over decades to centuries. Long-term effects, orbital evolution, resonance shifts, happen over thousands to millions of years. Very long-term effects, major dynamical changes, happen over tens of millions to billions of years. Earth's orbit would shift immeasurably if Venus disappeared today, but over 100,000 years, the shift would accumulate. Over millions of years, Earth's entire orbital history would diverge from what it would have been with Venus present. Understanding timescales is crucial for predicting consequences. Some effects are immediate and obvious, losing Venus from the night sky. Others are subtle and cumulative changes in Earth's orbital eccentricity cycles. Stability is a long-term concept. The solar system appears stable on human timescales. Planets follow predictable orbits for centuries. But on million-year timescales, stability becomes more nuanced. The current configuration is metastable, stable for long periods, but not forever. Mercury's orbit might become chaotic in 1 billion years. Removing planets could tip the system toward instability sooner. Computer simulations show that many solar system configurations become unstable within millions of years. Planets collide, get ejected, or have orbits drastically altered. Our solar system has survived 4.6 billion years, suggesting it's in a particularly stable configuration. Removing planets disrupts this stability. The remaining planets must adjust to a new gravitational environment, and that adjustment might reveal instabilities that were previously suppressed. Some planets are more essential than others. If we rank planets by how essential they are to solar system stability, Jupiter tops the list. Removing Jupiter would fundamentally alter the system. Saturn comes next, important but not as critical as Jupiter. Neptune is essential for Kuiper belt stability, but less important for the inner planets. Venus is surprisingly important for Earth's long-term stability. Mars and Uranus play supportive roles. Mercury is the least essential. This ranking reflects each planet's mass, location, and gravitational relationships. It's not a value judgment. Every planet is scientifically valuable. But from a purely dynamical perspective, some planets are more central to the system's structure. The system is interconnected. Perhaps the most important lesson: everything is connected. Every planet affects every other planet, even if weakly. Remove any planet, and ripples propagate through the entire system. This interconnection is subtle. Earth doesn't directly feel Neptune in any obvious way, but Neptune affects Uranus, which affects Saturn, which affects Jupiter, which affects Earth. The chain of gravitational influence links everything. The solar system is not a collection of independent orbits. It's a dynamical system, a network of gravitational interactions that have evolved together over billions of years. Disturb one part, and the whole system responds. Removing multiple planets. We've focused on removing one planet at a time. But what if we removed multiple planets? The effects would compound and interact in complex ways. Removing both Jupiter and Saturn would leave the outer solar system without its gravitational anchors. Uranus and Neptune might become unstable, and the asteroid belt might collapse into a planet. Removing Venus, Earth, and Mars would leave a large gap in the inner solar system. Mercury would be isolated, and the asteroid belt would have no inner boundary. Removing all the giant planets, Jupiter, Saturn, Uranus, Neptune, would create a solar system of only rocky planets. The asteroid and Kuiper belts would be unshepherded. Comet impacts on Earth would increase dramatically. Each combination would create a different solar system with different dynamics. The possibilities are vast, and predicting outcomes becomes increasingly difficult as we remove more planets. The role of moons. We've mostly ignored moons, but they matter too. Removing a planet removes its moons. Earth's moon stabilizes Earth's obliquity, helping maintain climate stability. Remove Earth, and the moon goes too. But if we could somehow remove just Earth and leave the moon, the solar system would have a new, large satellite orbiting the Sunday. Jupiter's moons, particularly Io, Europa, Ganymede, and Callisto, are worlds in their own right. Europa and Ganymede might harbor subsurface oceans. Removing Jupiter removes these moons, eliminating astrobiological targets. Saturn's Titan and Enceladus, Neptune's Triton, Uranus's Miranda, all are scientifically important. Their removal represents a loss beyond just gravitational dynamics. Thought experiments teach us about the real system. These thought experiments, imagining planetary removal, help us understand how the real solar system works. By seeing what happens when we remove a planet, we learn what role that planet plays. Jupiter shields the inner planets from comets. Venus helps stabilize Earth's orbit. Neptune controls the Kuiper belt. Each planet's role becomes clearer when we imagine its absence. This understanding has practical applications. When we discover exoplanetary systems, planets around other stars, we can predict their stability by analyzing their configurations. Systems lacking a Jupiter might be less stable. Systems with too many giant planets might be chaotic. Our solar system is just one example of planetary architecture. Thousands of exoplanetary systems show us the range of possibilities. Hot Jupiters, super-Earths, systems packed with planets in tight orbits. Each configuration has different stability properties. Studying planetary removal, even as a thought experiment, helps us understand planetary dynamics in general. It's a window into how gravity, resonances, and time shape planetary systems everywhere. We've journeyed through a series of thought experiments, removing each planet from the solar system and exploring the consequences. What have we learned? First, the solar system is a delicately balanced gravitational system. Every planet contributes to that balance, even small Mercury. Remove any planet, and the balance shifts. The effects might be subtle or dramatic, immediate or long-term, but they're real. Second, Jupiter is the solar system's keystone. Removing Jupiter would have the most far-reaching effects, altering the orbits of all other planets, transforming the asteroid belt, removing the comet shield, destabilizing the outer system. Jupiter's mass and position make it uniquely important. Third, even minor planets matter. Venus helps stabilize Earth's orbit over millions of years. Neptune controls the Kuiper belt. Mars contributes to inner planet dynamics. Each planet, regardless of size, plays a role. Fourth, the solar system's current configuration is the result of billions of years of gravitational evolution. Planets have settled into orbits that work together, creating long-term stability. This configuration is somewhat special. Many possible configurations would be unstable. Fifth, planetary removal would have cascading effects. Remove Jupiter, and Saturn's orbit changes, affecting Uranus, affecting Neptune, affecting the Kuiper belt. The system is interconnected, and disturbances propagate. Sixth, timescales matter. Some effects happen quickly, others unfold over millions of years. Understanding planetary removal requires thinking across vast timescales, from seconds to billions of years. Seventh, we're part of this system. Earth's climate is influenced by orbital variations driven by other planets. Jupiter protects us from comet impacts. Venus helps keep our orbit stable. We're not isolated, we're embedded in a web of gravitational relationships. As you drift towards sleep, imagine the solar system as a cosmic mobile, a delicate sculpture suspended in space, each planet hanging from invisible strings of gravity. The mobile has been spinning for 4.6 billion years, each piece influencing the others, creating a balanced whole. Now imagine reaching out and removing one planet. The mobile shifts, adjusting to the missing piece. Some parts move dramatically, others barely at all, but the entire structure responds. The balance changes, and the mobile spins differently, forever altered. Jupiter, the massive centerpiece, dominates the mobile. Remove it, and the entire structure might collapse. Venus, close to Earth, stabilizes our piece of the mobile. Remove it, and Earth swings more wildly. Neptune, at the edge, controls the outer reaches. Remove it, and the edges fray. Each planet has a place, a purpose, a role in the cosmic dance. Some are essential, some are supportive, but all are part of the whole. The solar system is not just a collection of worlds, it's a system, a family, a gravitationally bound community. We live in this system, on a planet whose orbit is shaped by Venus's pull, stabilized by the Moon's presence, and protected by Jupiter's shield. Our seasons, our climate, our very existence depend on this gravitational web. The thought experiments we've explored tonight, removing planets one by one, teach us to appreciate the system as a whole. They show us that stability isn't guaranteed, that the current configuration is precious, that we inhabit a finely tuned corner of the cosmos. Rest well, knowing that the solar system's planets are all where they should be. Jupiter guards the outer reaches. Venus partners with Earth. Saturn and Neptune maintain the distant regions. The mobile spins on, balanced and beautiful. Tomorrow, the sun will rise, and the planets will continue their ancient orbits, each pulling on the others, creating the stability that makes life possible. The cosmic dance goes on, uninterrupted, as it has for billions of years. Sweet dreams of orbital resonances, of gravitational partnerships, of planets working together to maintain the delicate balance. The solar system is whole, complete, a masterpiece of gravitational architecture, and we are here to witness it, living on one piece of the mobile, grateful for all the others that keep our piece stable, safe, and spinning through the cosmos.